We are working on a new section, the second section of chapter 3. So my goal is, if we can, to try and get chapter 3 finished today, or at least have a big chunk of it done. So quick overlap. We are only going to be essentially talking now about straight lines and scatter plots that have straight lines going through them. Here's a pretend story about the age of an animal and its weight, and here's a nice straight line. The textbook is going to be using, I think, the name regression line. So if you see the word regression line, they're talking about this line. Remember, we talked about all the other different names that they have for that same line, just in case you look at a video or something and they use a different term. I've made up a formula for it. The predicted weight of the animal is 5 plus 2 times its age. That's fine. We're going to, in a few minutes, focus on correlation coefficient, which is a number that tells you how good the data is to being a straight line. And we have talked about that. We're going to do more detail. And that's typically going to be written as a decimal. And a guy that I don't know if we mentioned him, but if we did, it would only be fleetingly. There's another guy called R squared, which isn't a coincidence because R squared is the square of this guy. So if this guy is 0.2, this guy is going to be whatever 0.2 times 0.2 is, right? 0.04, right? It has a name, although I don't think the WebAssign mentions it. It has a name. It's called the coefficient of determination, if you're interested. And it's normally written as a percentage. I think one of the reasons they write it as a percentage is just to make it enough difference between the two so you don't kind of get confused. If you see a percentage, they're almost always talking, they're not. They are talking about R squared. If you see a decimal, they are talking about R, right? And these two guys, the R value and the R squared, are what is called independent of the units used. So can you imagine that I got the age of the animal, but instead of doing it in months, I did it in years. And instead of the weight being in pounds, I changed it into ounces or kilograms or something else. Although the data points would be different and the equation of the line would be different, surprisingly, the correlation coefficient will be the same number, whether you use ounces and pounds and feet and miles or any other unit under the sun. It's still the same R value and the R squared, obviously, for the same reason. So, quick reminder and some adding. What does R and R squared tell us about how strong the data is? Well, let's look at the correlation coefficient R. It takes a number somewhere between -1 and 1. So if somebody says, oh, yeah, I did a calculation and I got an R value of 1.4. They're either lying to you or they got it wrong and they don't even know that they've got it wrong, because the biggest value in R can be as 1 and the smallest it can be is -1. And to remind you, isn't an R value of 1 a perfectly positive straight line, right? And an R value of -1, wouldn't that be a perfect straight line going that way? And an R value of 0 would be a big circle of nothingness. We comfortable about that? We've talked about it before. Feel good? Now, R squared is what you get when you take R, right, and you square it. That makes sense. So that makes R squared guaranteed to be between 0 and 100. Why isn't it between -100% and positive 100%?
The square of a negative is a positive.
Right. So if the R was -0.8, when you square it, don't you get positive 0.64, which then becomes 64%. So if someone says to you, I've got a scatter plot and the R squared was 80%, that's pretty good, right? 90% even better, right? If they said it's 120%, aren't they lying or they don't know they're wrong, right? You can't get 120% or -5% for the R, right? Now, the R value and the R squared value kind of share they tell you the same kind of thing, right? They tell you in their own way. This guy loses some information. If I tell you that the r squared is 100%, all you know is that it's a perfect straight line. What you don't know is it a positive or a negative association? Agreed? If, you know, that is what it is. Now, if I tell you r squared is 0%, don't you know that it's a big fat circle with nothing going on, right? So that's still true. We go? Yeah. Suppose I have a question and the r value is 0.8. Then the r squared value is 0.8 squared, but we take that decimal and we convert it into 64%. Are you comfortable with the calculation of r squared? Unfortunately, if you do it the other way around, you have a problem. Suppose I tell you r squared is 81%, and I'd like you to figure out what r is. This is the problem. First thing you need to do is turn it into a decimal. Turn it into a decimal. What will I now do to find r?
You square it.
You may be using the wrong word, but you're
Square root.
the right thing. Square root. Is that what you meant to say? Square root. I hope you did anyway. I'm bouncing about here because I got some background noise I'm trying to kill off. There we go. So you would take the square root of 0.81, which is nothing 0.9. But here's the problem. Yes, it could be 0.9, or could it equally have came from a negative 0.9? If I give you an r, aren't you guaranteed to get the right answer? There's only one right answer for r squared. If I tell you what r is equal to, there's only one correct answer for r squared, right? You're going to get that right. But if I tell you r squared, isn't there two possibilities typically? So if you get a question like that, you know, one of those ones that they give you 5 answers to pick from, one of the answers will just say 0.9, but the other answer will say negative 0.9 or positive 0.9. You see, that's the one you should pick in this question. Now, when you are told r squared, a lot of textbooks, and hopefully somewhere you'll read it in this book, let's suppose I tell you that r squared was 81%. And you're saying, well, what does that tell me? Well, one of the things it's telling me is that that's a pretty good fit. Agreed? 81% is pretty good. Its official phrase that we would use in statistics is that 81% of the variation is accounted for by the model. Now that's a very lawyer-esque sentence, but that's a sentence that you might see from time to time. So 81% of the variation is accounted for by the straight line. The model's just a straight line. In English, I think of it more like this, although it's not 100% equivalent, it's close enough. If you get an r squared of 81%, doesn't that mean that you're like 81% right? In other words, if you pick a random dot, isn't there a good chance, 81% chance, that it's either on the line or damn close to it? In other words, there's almost no error. Right? Suppose I went and said to you that I had a straight line and r squared was 10%. Wouldn't that kind of mean 10% of the time I'd get the right answer? But isn't the opposite true? 90% of the time, it'll be miles away. Can you see why that's a bad fit? 81% of the time, it's pretty much the right answer, give or take a little. 19% of the time, you're going to be wrong. On the other hand, If it was 100%, wouldn't you expect it to be a perfect fit? In other words, whatever it predicts should be the right answer. And so it's a very good measurement of how well your data is to fitting. So if someone comes up, and this is me kind of changing the story a little bit, but I want to show you a very important sentence and what it means. And that sentence is, correlation is not causation. A lot of people think that because they've got a nice scar plot and it's a straight line, that the first thing, right, is making the second thing happen. Here's an example of something that is true that kind of proves my point. If you go and you collect data on countries in the world, so every one of my dots is a country in the world, right? And you put along here the average number of televisions in a household. So in a place like America, would you agree that the average number is probably over 2? Because you have your TV, but don't you have another one somewhere else for the kids to watch TV because you don't want to watch what they're watching, right? So there's a good chance there's quite a few TVs. And then on this side, so that's the average number of televisions. And on the y-axis, I'm going to pay to their life expectancy. And when you plot the average number of TVs that a country has and their life expectancy, you will get a pretty decent straight line. And let's just say, for argument's sake, the R squared is 81%. That's how good it is. Then people make this mistake. The number of TVs that you have increases that country's life expectancy, right? The average age that person lives. Would you agree that's totally stupid? How many TVs you got does not make you live longer. So the correlation is there, but not the causation. What do you think we're measuring when we measure number of TVs against life expectancy? Any ideas? A country's got a lot of TVs. People in that country. Wealth, yeah. Would you agree if a country on average, every household's got about 3 TVs, would you agree that country's probably very rich or very weird? More likely very rich, right? What do you know about rich countries? Well, rich countries, don't people who live in rich countries, generally speaking, have more food than very, very poor countries, more access to healthcare, more medicines that they can get. They live in better houses, so they don't end up like freezing to death or burning to death. They have good water, not bad water. All those things that rich countries have and poor countries have less of. Don't those things contribute to you living longer? So TVs are not making people live longer. TVs is just a measurement of a country's wealth, and country's wealth is the real factor connecting to the life expectancy. See if this was truly correct, see if this was really true, wouldn't the world be able to fix life expectancy by making lots of TVs and sending them to poor countries? And you see how silly that argument would be. Now, what happens, and it happens a lot, is that people don't think that through. And they see increase in this causing increase in that, therefore this increase is causing that increase. And it's not necessarily so. So always be careful. If someone jumps from good scatter plot, nice straight line to saying this thing, whatever X is causing Y thing. Say to them, you know that correlation is not a guarantee that it's causation. The number of times that we have been caught out on that connection, it's not good, right? Are we okay with that concept, just in case it pops? Right. Let's talk about some questions then. Some of them are pretty quick, so that's good. We should be able to go through them, I hope, relatively fast. Right, I'll make this a bit bigger. Okay, which of the following numbers cannot be a correlation coefficient? You could have said, which of the following numbers could not be R? And there could be more than one choice. Can anybody see a number in that list that's not allowed to be R? Tell me it, just share it out.
-1.3.
Because it's less than -1, agreed. Is there another one? Because I can see another one.
2.3.
2.3. Yeah, that was easy. Now, be careful. R squared, right? Now, R squared can be written, and it probably is going to be written as a percentage, but before it became a percentage, couldn't it be a decimal? So don't get caught out with that. Okay, give me a number in there that definitely cannot be R squared.
Any of the negative values.
Okay, so we'll kick out -50 and -2.5. Okay, is there any percentage ones that can't be R squared?
200%.
Right. Now it gets a little bit sneakier. Which one of the decimals that's left also cannot be R squared?
1.7.
Agreed. If you take a number that's between -1 and 1 and you square it, don't you always get an answer that's less than 1? Actually, between 0 and 1. Now, let's get this question right. Refer to the values in part A. So that's these ones here. Which one of the legitimate values, so don't pick any of the ones we crossed out, represent the strongest relationship? Okay, of the 4 guys that are left, which one of those 4 is the strongest relationship, the closest to being a straight line?
1.0.
Agreed, 1.0, Rob. Right, see how quick those questions are? Nice and smooth. We're doing them together, that's fine. Gonna have to shrink this back because there's a whole load of reading going on. For 188 students, the correlation between the fastest speed ever driven and a number randomly picked between 1 and 10 is about R equals 0, which it would be, right? Why should a random number have anything to do with how fast you go? Okay. Describe what this correlation indicates about the association. Well, if an R value is 0, which one of these 4 sentences would you be able to choose as closest to reality?
It's not linear related.
Okay,
The last 2.
that one there.
Yes, it's one of those 2.
Right. So they're not linear related, check. The one above it says, a scatter plot will likely show a pattern with most of them following a straight line. No, won't it likely show you no pattern? Which is why it's the 4th one. Question 4, suppose that R squared is 100. Which of these sentences describes it?
It's a perfect linear relationship.
Agreed. What are the 2 possible values for R? Right, I know they're calling it the correlation coefficient, but that is R, right? What are the 2 possible values for it when R squared is 100%?
Plus or -1. So the 4th option.
That makes sense, everyone? R is always a decimal. R squared is typically a percentage, but technically you can have it as a decimal, but typically a percentage. Now here's a question to do with R again. Female bears, and even give you a data set on them, the correlation between the length of the bear and, you know, if you're doing a tape measure right around the chest, is 0.82, right? Okay, R equals 0.82. Describe how the chest girth will change as the length increases. Now, since that is a positive correlation coefficient, doesn't that mean that the line goes uphill? So if the length gets bigger, won't the chest girth get bigger? So you pick the sentence that does that. This one's a little bit sneaky. It says, which is the strongest relationship? R is positive 0.2, or the R is negative 0.8. Be careful. Which one of those two is the stronger relationship?
Negative 0.8.
Isn't that closer to being a straight line that just happens to be pointing downwards? We don't care which direction the line points, right? That's nothing to do with its strength. So I agree with you. In this figure below, we are looking at right-hand span of colleges and left-hand spans. I would have thought they're the same, but evidently there's a little difference. But the correlation coefficient is really high. I agree, 0.95 is darn close to perfect. What would the correlation value, the R, be if you took all these units that were in centimeters and decided to remeasure them in inches? And we've mentioned that at the start of today.
The correlation wouldn't change. The number would be the same.
Right. Remember I said that sentence, it's independent of units. That's the question that's kind of testing that, right? Which is really good. Isn't it good that it doesn't matter what you measure the things in, the strength is still the same, even if visually it looks different. That's because, do you know when you do scatter plots, if you change the scale, can't you make things look really further apart or really close together if you make the scales big or small? Do you see how the correlation coefficient doesn't care what the scale is? It tells you the truth regardless of how you draw it. Because I've seen scatter plots. For instance, for me, that doesn't look very much like 0.95. To me, that looks more like it should be a little bit less than that, like a 0.9 maybe. But that's just my eyesight. It's not that it isn't 0.95. But can you see that if I chose a different scale, couldn't I crunch it more? Yeah, I could make my sausage skinnier, for want of a better word. That's why visuals are not as good as numbers, right? R doesn't care, it's the same number all the time. That's much better. And there's a little sentence that you can go into. The figure below shows 4 graphs. 1, 2, 3, 4, agree. And all the scales are the same. That's important, so we don't get distracted by the scales. Which of these 4 is the strongest relationship to being a straight line?
Graph 2.
Agreed. Now, a lot of people will look at graph 3 and say, well, it's very symmetric. It's a rectangle, which it is. But it's not a very good single straight line, is it? Well, not as good as that one is. Agreed. Which one of those 4 is the worst, really, the worst relationship?
Number 4.
Why? You're right. Why?
Because it's almost a complete circle.
Yeah, big blob of nothingness, right? Now we have a bit of a problem because I'm not 100% sure I know my answer either. If graph 2 is the best and graph 4 is the worst, you've got graph 1 and 3 left over. If you had to decide between 1 and 3, which one of those 2 is closer to being a straight line?
I would go with graph 1 over graph 3. It's got that sausagey shape to it. It's just expanded. It's moderate.
Okay, I agree. I don't think they asked you that question, but it would have been nice if they had. Oh, here's another bunch. Oh, now this is a little bit different, and I like different. Same kind of shapes, but now they've got an R value to go with them. So which one of those four guys is negative 0.9?
2.
You all agree with that? Okay, so that one's out the window. You can't use negative 0.9. Which one of those four guys is 0?
4.
Okay. Now we've got a 0.3 and a 0.6. Based on what we just asked a few minutes ago, which one of those, graph 1 or 3, is going to be the slightly better, the 0.6?
Graph 1 is the 0.6.
Yeah, that's what I'm going for, and then part the other one. You might think 0.6 is good, and it's kind of moderate, really. If you do 0.6 and you do it square, you know, you do the R squared value, isn't it only 36% of the data is going to be close to the line? So 1 and 3 is good, but aren't the other 2/3 going to be, you know, pretty far away? Probably not so good. Okay, got it, Mason. Now, what's this one? Oh, we've already answered these. Okay. Question 10. A data set on body temperature gives age in years, okay, against body temperature. I'm going to do that as a little picture for my own benefit. This is your age in years. And then vertically, it's a body temperature. And the body temperature is in degrees Fahrenheit. Okay. And it's for 100 blood donors in the age range 17 to 84. Okay. The data shows a correlation of negative 0.312. Okay. Negative 0.312. Use this value to try and characterize the relationship. The value indicates that as the age goes up, the average normal body temperature goes down. Why does that? How do I know that?
Because it's a negative correlation.
Yep, that's pretty much it. Negative 0.3 is negative. Doesn't that mean it? No, right? As one gets bigger, the less. Right. With okay, what do you think a 0.312 is? Oh, they've put in, instead of moderate, they've put in somewhat. What you going for?
Somewhat weak.
Yeah, and if that one doesn't work, I'm going to go for even weaker than that, right? You know, you get 5 shots, so you're going to get the right one eventually. Okay, next question is, for each pair of variables, identify, is it going to be positive, negative, or none? Okay. The verbal skills and age for children under 12. So you're going to have their verbal skills and their age. So it could be 8, 9, 10, 11, 12, and how good their verbal skills are. What would you go for that one? Well, let's see. On average, the verbal skills of children under 12 tend to improve as children get older. Would you agree? And because it tends to improve, doesn't that make it a positive correlation? I mean, they're trying to help us here, right? What about, on average, the adult height of a firstborn twin tends to be the same as the second-born twin. Thus, we would expect this pair to have no strong correlation. Nothing's perfect because they are identical. Would you agree the identical helps a lot? Because there's, you know, there's not going to be much difference between the two. Okay, the number of dogs and the number of fire hydrants. Oh God, who thought this question up? On average, as cities grow, the number of dogs tends to increase. Would you agree that a city with 1 million people has probably got more dogs than a city of 100,000, right? So, okay. And the number of fire hydrants also tends to increase. Would you agree a city of 1 million probably has more fire hydrants than a city of 100,000? Thus, that means a positive correlation. Now, if you took that to its silliness, wouldn't that mean that the more dogs you have, the more fire hydrants you're going to have? But do you think the fact that there are more dogs is why the city builds fire hydrants? Do you think they just build them for them so we can pee on them? No, do you see it's not the real cause? The number of pairs, we'll let you do that one. Okay, moving on. If you know that R is 0.3, right? And this is the height and weight of 12th grade male students, it's 0.3. Then want this guy rounded to 2 decimal places is important. So they want it to be 0.3 times 0.3. Can you trust me that that's what the answer is as a decimal? Because they said to 2 decimal places. Now, if they wanted it as a percent, wouldn't I put 9% in? How do you know when the WebAssign wants a percent and when it just wants a decimal? Isn't there typically a little percentage here at the end so you don't need to type it in? Sometimes you have to do, because you end up doing the question right and then you figure out why it's not giving you the answer. I'm assuming that. Now, choose a sentence to interpret R squared. It's this one. Remember that sentence that I wrote down? They've just rearranged the words. The variation height explains 9% of the variation. That's what that is about. Because isn't that guy 9%? Now, suppose that they did the same data, but they collected it in meters or kilograms. Won't that still be the same number? And here's another one to do with sleeping hours. And here is 14 now. I'm going to have to shrink this back a lot because we have a city, the latitude and the temperature. They've used this data for all sorts of things. And we are going to find the correlation between average January and latitude. So all we're going to do in this question is figure out what that answer is. And there's a little guy up here that I'm going to use as well later on. They're telling me that R squared is 73.3%. And I'm going to do this guy using salt, and then I'm going to show you how I can do it without using salt. Because this question, you could do it 2 ways. So I'm going to hit this one. That's good. And I am going to hit charts and graphs. I'm going to hit scatter plots. And it's going to be latitude against January temperature. And the only guy I'm interested in is, can you see that correlation coefficient of negative 0.856, which is this guy here. Did you see how I got it? We go with that. Now, darn it in space. Can I go back here? Please let me go back. I want to go back. I can. Here we go. Here is our question. The answer that we got was, using salt, negative 0.856 to 2 decimal places, okay, 86. Now I'm going to show you a different way of getting that same answer. We were told that r squared was that guy, right? And then if you turn that into a decimal, isn't r squared that guy? If you want to find r, don't you take the square root of that guy? And the square root of 0.733 ends up being 0.856, 0.86, agreed? Well, wait a minute, or negative 0.86. We know it's going to be one of those two. Now, I don't want to go back and forward again, but remember with the table here with the latitude and the temperatures? If I looked at that table, wouldn't I notice that this was going down the way? And therefore, it would be negative. And that's why I would have chosen that one. Does that make sense of how I could have done it without even using solve? Just use the table and says, oh yeah, as the latitude increases, the temperature goes down. So that means it's a negative R value, right? It's decreasing. Let's pause for a minute. Any questions so far? Because I've ranted on for too long and not give you a chance to chuck in here. Anything we've done in the last few, whatever, that you want me to talk about? Is it going pretty smoothly? Okay, then let's return to where we were. Okay, where are you? I just got too many windows open now. I can't find anything. There we go. Oh, that is a really good question, but I don't want to use it up. I'll give you a clue to it. It'd be unfair just to dump you at it. Here is a sketch of a scatter plot where the correlation without the outlier is negative. But when you add the outlier, it turns into a positive. Okay, so each one of these has got an outlier. I want you to imagine that the outlier has disappeared for a second and just look at the dots that are left and see whether we can get a negative association, right? If that outlier disappeared, would you agree this data is positive? So it ain't that one. If this outlier disappeared, would you agree the data is negative? If this one disappeared, would you agree it's positive? We'll forget that one. If this outlier disappeared, would you agree it's negative? So what we're left with here are some data with an outlier here and some data with an outlier here. Now, if you include the outlier, how does that affect the line? Well, outliers are like Bill Gates. They can change everything if they're big enough. I want you to imagine the outlier is like a really strong magnet and that the line is a piece of metal. If the strong magnet is strong enough, won't the line bend towards it? So you can see a line that's like this might actually bend positive if the magnet was strong enough. So if we look at this one here, can you imagine the metal, the line is here and the magnet's here. Won't it bend it a little bit towards it, but won't it still be pointing downwards? So it's not this one. Now remember the other choice was that one. See this outlier here? Can you imagine the straight line being bent upwards towards it? So that would make it that one. So I guess I did do it after all, but it's kind of hard to think that one through. Okay, question 16 is very like this one up here, so I'm just going to skip by it. Just quickly reading through this question because I'm not sure what the heck it's doing. Okay, here we go. Suppose a regression line equation, X is the putting distance, right? And Y is your success rate, right? So the percentage of the time that you put the ball into the hole is 76.1, take away 3.94 the distance. So you can imagine the further away, the less chance you have of putting it, right? Use this equation to predict what it would look like at 2 feet. Right, can you imagine just doing this calculation? 76.1, take away 3.94 times 2 feet. And since that's a pretty quick question, I'll do that. 76.1, take away 3.94 times 2. And the answer I get is about 68, there we go, 0.22. Okay, you got about 68% chance of making it. Now, if it's 20 feet away, do you think it's going to be a smaller percentage chance of potting it? Yeah, you're 2 feet away, you get about 68% chance of doing it. What about if you were 20 feet away? What's your chances now? You agree it's less? Right, in my calculation, you just trust me on this, the answer ends up being something that is remarkably silly. Your chances of potting or putting or whatever you want to call it is negative 2.7. What on earth does that mean? Can you get a negative percentage chance of doing anything? The chances that I win the lottery are negative 2.5%. That does not make sense, does it? Isn't the lowest you can get is 0? Probabilities, right? 0. So if you wanted to make that realistic, I guess you could put in 0. But what that in fact is doing, oh, last thing for today, what that in fact doing is showing us a problem with linear regression. So let me show you right now, and we'll call that the last thing. While I'm doing that, will you put your last name space first name? Do the attendance. Can we just pretend for argument's sake that if you take someone's age against their height, that it's pretty linear? In other words, as you get older, you get taller, right? And let's suppose that the predicted height of someone is 10 plus 5 times their age. 5 is probably too big a number. 3 times their age. And that model works really good for people up to about the age of 19. Right? Pretty good. Not perfect, but pretty good. Suppose I use this formula for a 90-year-old man. Can you see that that model is useless? If you only collect data from 1-year-olds to 19-year-olds and it's nice and straight and linear, you can use it to predict the height of any person between 1 and 19 years old and you'll be fine. But don't start using it for a 40-year-old person or even a 30-year-old person, because if you tried, can you see that you would end up with a number that doesn't bear any resemblance to reality? The reason for that is, doesn't basically the data level off? Don't you stop growing around about whatever, 19, 20, whatever? So the model isn't linear for eternity. Don't a lot of models grow and then they kind of level off, right? Horizontal. We were using the model as if the straight line kept on going. Can you see why a 90-year-old ended up with a stupid answer? Because the straight line was predicting 280 inches. They even have a name for that. So here it is. This phenomenon is don't use your line beyond the range of the data. It's called extrapolation, if you want the fancy word. So don't use your line with extrapolation, or at least be very suspicious of it. Extrapolation just means continuing into the future, right? Where you've not actually got any data, but you're still using the straight line to make predictions. That can't you can see why that could go really screwy on you really quickly. Unfortunately, a lot of people do that. Aren't we making predictions about the world's temperature in 100 years from now? But aren't we only basing it on data that we've collected up to now and assuming that that pattern continues? But what happens if the pattern doesn't continue? What happens if it cycles down? Won't your predictions be totally wrong? Now, if the pattern does continue, your predictions could be totally right. But isn't there a danger? I don't know what's going to happen in 100 years from now. Do you? If I knew that much, do you know I would have bought Microsoft when I was 20?